Hey friends, welcome to the YouTube channel All About Electronics. In this video, we will learn about R2R Ladder type of DAC. Now, if you have followed the previous video, we have discussed the binary weighted resistor type of DAC, and we have seen that as the number of bits increases, the range of resistors which is required for the DAC will also increase, and it is difficult to produce all these different values of resistor with a good accuracy. And we have seen that if these resistors are not accurate, then it can produce a significant error in the output. And this problem can be solved to quite an extent by using the second type of DAC, which is known as R2R Ladder type of DAC. So as you can see, this type of DAC uses the resistive ladder network, and this ladder network contains only two types of resistors. And this DAC has a certain advantages. The first is, as it contains only two types of resistors, so it is easy to fabricate these resistors with a good accuracy. The second is, as it requires only two types of resistors, so this circuit is easily scalable to any number of bits. And the third is, if you see the output impedance of this circuit, which is the Thevenin's equivalent resistance, then it is equal to R. And regardless of number of bits, this output impedance remains the same, and due to that it will not affect the other circuitry. So these are the few advantages of this DAC. Now before we move ahead, let me show you how the output impedance of this ladder network is equal to R. So here we will find the output impedance for this 3-bit ladder network. Now to find the equivalent resistance, let us assume that all the sources are 0. That means all these resistors are connected to the ground terminal. So after connecting all the resistors to the ground, if you see this portion, then these two resistors are connected in the parallel combination. So their equivalent resistance, that is R equivalent, will be equal to 2R in parallel with this 2R, that is equal to R. So we can replace these two resistors by the equivalent resistance of R. And if you see the equivalent circuit, then it will look like this. Now here, these two resistors are in series, and once again, this combination is in parallel with this 2R resistor. So the equivalent resistance will be equal to R plus R, and that combination is in parallel with 2R. So the equivalent resistance will be equal to R. And if you see the equivalent circuit, then it will look like this. Now once again, if you see over here, these two resistors are connected in parallel. So their equivalent resistance will be equal to R. And now if you see, these two resistors are in series, and that combination is once again in parallel with this 2R. So due to that, the overall output impedance will be equal to R plus R, that is in parallel with 2R, that is equal to R. So from this, we can say that the overall output impedance is equal to R. So regardless of the number of bits, the output impedance of this ladder network remains R. Now let us understand how this ladder network converts the binary numbers into the analog output. Now if you see this ladder network, then according to the binary numbers, these resistors are connected to either a reference voltage or to the ground terminal. So if the binary number is 1, then it is connected to the reference voltage, and if it is 0, then it is connected to ground. And using the switches, it is possible to change the connection between the reference voltage and the ground terminal. So the output of this ladder network will depend on the position of these switches. That means whether these resistors are connected to the reference voltage or to the ground terminal. And further, if you want to amplify the output, then it can be given to the amplifier circuit. So let us understand how we can find the output of this ladder network. Now this entire ladder network can be represented by the Thevenin's equivalent voltage in series with the resistor. And we have already seen that how we can calculate the Thevenin's equivalent resistance for the ladder network. And here the value of the Thevenin's equivalent voltage will depend on the position of the switches. So to find the Thevenin's equivalent voltage, what we will do, we will consider one voltage source at a time, and then using the superposition theorem, we will find the overall output voltage. That means we will assume that at a time only one bit is 1 and only one switch is connected to the reference voltage, while the other switches are connected to the ground terminal. And considering that, we will find the Thevenin's equivalent voltage. And then by using the principle of superposition, that means by combining the individual outputs, we will find the overall output. So here we will find the output voltage for this 3-bit ladder network. And here this B0 is the least significant bit or LSB, and this B2 is the most significant bit or MSB. So first of all, let us find out the output whenever the input code is 001. That means only B0 is 1. So in this circuit, first of all, let us find out the Thevenin's equivalent circuit for this portion while looking from this side. Now the same portion can be redrawn like this. Now in this circuit, the Thevenin's equivalent voltage VTH is equal to 2R divided by 2R plus 2R times V reference, that is equal to V reference by 2. And to find the Thevenin's equivalent resistance, let us assume that this V reference is equal to 0. So the equivalent resistance will be the parallel combination of these two resistors, that is equal to 2R in parallel with 2R. So the equivalent resistance will be equal to R. So let us replace this portion by the equivalent circuit. And now if you see the circuit, then the equivalent circuit will look like this. So once again, let us find out the Thevenin's equivalent resistance for this portion. So for this portion, the Thevenin's equivalent voltage VTH will be equal to 2R divided by 2R plus 2R multiplied by V reference by 2, that is equal to V reference by 4 volt. And to find the Thevenin's equivalent resistance, we will consider this voltage source as 0. That means the Thevenin's equivalent resistance will be equal to R. So if we replace this entire portion by the equivalent circuit, then the equivalent circuit will look like this. Now once again, if we find the Thevenin's equivalent circuit for this circuit, then the Thevenin's equivalent voltage VTH will be equal to 2R divided by 2R plus 2R times V reference by 4 volt, that is equal to V reference by 8 volt. And the value of the Thevenin's equivalent resistance will be equal to 2R in parallel with 2R, that is equal to R. So if you see the equivalent circuit, then it will look like this. So in this way, by finding the Thevenin's equivalent circuit, we can minimize the circuit and we can find the output voltage. So from this we can say that whenever only this bit B0 is 1, at that time the output of this 3-bit ladder network is equal to V reference by 8 volt. So similarly, let us find out the output whenever this bit B1 is 1 and the remaining bits are 0. So considering that, if you see the overall circuit, then it will look like this. Now if you see over here, these two resistors are connected in parallel, and the parallel combination of these two resistors is connected in series with this resistor R. So the equivalent resistance of these three resistors will be equal to 2R in parallel with 2R, and that combination is in series with this resistor R, that is equal to 2R. So if you see the equivalent circuit, then it will look like this. Now to minimize the circuit, let us find out the Thevenin's equivalent circuit for this portion. And this portion can be redrawn like this. So for this circuit, the Thevenin's equivalent voltage will be equal to 2R divided by 2R plus 2R times V reference, that is equal to V reference by 2 volt. And by considering this voltage source as 0, the Thevenin's equivalent resistance will be equal to R. So if we replace this portion by the equivalent circuit, then the equivalent circuit will look like this. Now once again, to find the output voltage, let us find out the Thevenin's equivalent circuit for this portion. So for this circuit, the Thevenin's equivalent voltage will be equal to 2R divided by 2R plus 2R times this voltage, that is equal to V reference by 4 volt. And considering this voltage source as 0, the Thevenin's equivalent resistance will be equal to R. And if you see the equivalent circuit, then it will look like this. That means for this 3-bit ladder network, whenever this bit B1 is 1 and the remaining bits are 0, at that time the output of this ladder network will be equal to V reference by 4 volt. And similarly, let us find out the output whenever this bit B2 is 1 and the remaining bits are 0. So in this circuit, these two resistors are connected in parallel and the parallel combination is connected in series with this resistor R. So the equivalent resistance of these three resistors will be equal to 2R in parallel with 2R, and that combination is in series with this resistor R, that is equal to 2R. So if we replace these three resistors by the equivalent resistor, then the equivalent circuit will look like this. Now once again, if you notice over here, these two resistors are connected in parallel and that combination is connected in series with this resistor R. So the equivalent resistance of these three resistors will be equal to 2R. And if you see the equivalent circuit, then it will look like this. So here, to find the output voltage, let us find out the Thevenin's equivalent for this circuit. And the same circuit can be redrawn like this. And we already know that the Thevenin's equivalent voltage for this circuit is equal to V reference by 2 and the Thevenin's equivalent resistance is equal to R. So from this we can say that whenever this bit B2 is 1 and the remaining bits are 0, at that time the output of this ladder network will be equal to V reference by 2 volt. So from this we can say that whenever this bit B2 is 1, at that time the output of the ladder network is equal to V reference by 2 volt. Similarly, whenever this bit B1 is 1, at that time the output is V reference by 4, and similarly whenever this bit B0 is 1, at that time the output of the ladder network is equal to V reference by 8 volt. And whenever more than one bit is 1, at that time the output will be the summation of individual outputs. For example, when all the 3 bits are 1, then the output will be the summation of individual outputs, that is equal to 7 by 8 times V reference. So in general, for the 3-bit ladder network, we can say that the output voltage V out will be equal to V reference times B0 by 8 plus B1 by 4 plus B2 divided by 2. Or in general, the output of the ladder network can be expressed by this expression. So let's say the output of the ladder network is equal to VR 2R. And if this voltage is given as an input to the op-amp, then the input to the op-amp will be this voltage in series with this equivalent resistor R. So if you see over here, the op-amp is configured in the inverting configuration. And for the inverting configuration, the output voltage V out will be equal to minus RF by R times this voltage. So in general, for the n-bit ladder network with op-amp, the output voltage can be expressed by this expression. And if we further simplify it, then it can be expressed by this expression, that is minus V reference times RF divided by R with summation of 0 to n minus 1 Bi divided by 2 to the power n minus I. So here n is the number of bits and I is varying from 0 to n minus 1. So here the value of RF and R decides the gain of this DAC, and the reference voltage will also get multiplied by the same factor. So if RF is equal to R, in that case the gain of the DAC is equal to 1. And for the unity gain, instead of this inverting amplifier, we can also use this buffer amplifier. So with this buffer amplifier, the output will be in same phase with the input voltage. And for this circuit, in general, the output can be expressed by this expression. And if you further simplify it, then it can be expressed as V reference times summation of 0 to n minus 1 Bi divided by 2 to the power n minus I. So in this way, by using this R2R ladder network, we can convert the binary number into the analog output. So by connecting the resistors in this ladder form, we can also design this type of DAC. But the values of resistor should closely match with each other, because if there is any mismatch, then it can produce the error in the output voltage. But whenever these resistors are fabricated in the IC itself, then their values are closely matched and it is possible to achieve the high resolution. So commercially, this type of DACs are available starting from 6 bits to the 20 bits. Alright, so now let's take one example based on this type of DAC. So in this example, we have been given this R2R ladder type of DAC and we have been asked to find the full scale output voltage of the given circuit. And also we have been asked to find the output voltage corresponding to this code. And here we have been already given the value of this RF, R and the V reference. So we know that for the R2R ladder type of DAC, the output voltage Vout can be given by this expression. So here we will get the full scale output voltage when all the bits are 1. And if you closely observe, this given circuit is a 6-bit DAC. So considering all the ones, the output voltage or the full scale output voltage will be equal to 5 volt multiplied by minus RF divided by R or minus 2 by 1 times summation of 1 divided by 2 to the power 6 to the 1 divided by 2 to the power 1. So if we simplify it, then the full scale output voltage will be equal to minus 10 times 63 divided by 64, that is equal to minus 9.84375 volt. So this will be the full scale output voltage. Now let us find out the output corresponding to this code. So if you observe over here, only 3 bits are 1, that is B5, B3 and B2. So the output voltage Vout will be equal to minus 5 times 2 by 1 multiplied by 1 divided by 2 to the power 1 plus 1 divided by 2 to the power 3 plus 1 divided by 2 to the power 4. So using this expression and considering these 3 bits as 1, we can write this expression. And if we simplify it, then we can say that that is equal to minus 10 times 11 divided by 16, that is equal to minus 6.875 volt. So in this way, if we have given the binary code, then we can find the output voltage for this given DAC. And in the same question, suppose we have been asked to find the resolution of the DAC, then we can find that too. So in the comments, do let me know what is the resolution of this 6-bit DAC. So that's it for this video, and I hope in this video you understood what is R2R ladder type of DAC. So if you have any question or suggestion, do let me know here in the comment section below. If you like this video, hit the like button and subscribe to this channel for more such videos.